Hello and welcome back to Physics for the 21st Century. Again, my name is Greg Perugini, and today's topic is torque and equilibrium. So when we talk about torque, we're talking about force rotationally. If you remember, we talked about force F equal ma. Rotationally, we can't use just mass. We have to take into account the object's geometry. So we have to use moment of inertia times the rotational acceleration, rads per second squared. So if we're doing problems that are rotational, and I have my radius whatever it might be, let's say it's 0.5 meters, I may have a velocity that's caused by a force, and this is in meters per second, and as we saw before, I can do velocity is equal to rads per second times the radius. I can know that acceleration is equal to alpha, the same alpha that we have here, times the radius. Okay? And so, as we look at that, the spin that we're going to be talking about that is caused by torque, this is like a seesaw type of example, would be a force that we would place. And what's going to happen to the seesaw? Well, intuitively, you're going to see it go in that direction, right? Well, that is negative torque. And that torque here, this particular torque, is this radial arm times the force. And in this case, it'd be the force of gravity. Let's say this is a person sitting here or whatever it might be on this seesaw. And his mass in kilograms times gravity on Earth times this radius, how far from the pivot, would be this torque in this direction. If I wanted this to balance, the summation of all the torques in balance must equal 0. So I necessarily have to have someone over here at some distance from the focal point, right, causing a force downward that is going to have a spin of torque in the positive direction. So the negative and the positive, if this is a balanced seesaw, the negative and the positive would net out to 0. So, we have positive torque in the counterclockwise direction, counterclockwise, and a negative torque in the clockwise direction. Torque is equal to the force times the distance times sine of the angle. We'll get into what we mean by sine of the angle in a minute or so. So, as always, it's probably best to look at an example here. Say we have a 2 kilogram weight. And it is 0.5 meters away from this fulcrum. And let's not worry about the mass of the bar. Let's just say it's evenly distributed. And we want this to balance. So to have it balance, of course, we want the summation of all the torques to be equal to 0. So how do we go about that? How do we get that to happen? Well, if the summation of all the torques equals 0, then this is causing a negative torque. So if I have, let's give a weight here, let's say a 3 kilogram mass on this side, we want to know how far from the fulcrum that weight has to be for this to balance. So it's an interesting problem. So what we have is this in the negative direction. We can just say negative 2 times gravity times 0.5. And then we have in the positive direction 3 times gravity times, well, we don't know, the radius. But if we want this to balance, it all has to equal 0. So we solve for r. So if we do this math, this is a negative, this is a positive. If you want, you could put that on that side. Do the math. You get something like at 0.33 repeating meters. So that is where that has to sit. Now let's look at another thought here. What if I am pressing on an angle? Let's say I'm applying 40 newtons at an angle. Well, if I'm applying 40 newtons at an angle, then that's where the sine of the angle, I have in a sense diluted my force. It's not nearly as strong as if I was perpendicular. It is at an angle, and let's give this an angle of, say, 50 degrees. Well, I have it already figured out at 40 degrees, so let's go with that. And that we're 2 meters from this edge. So the torque that is caused by this force at this angle would be force times the radius times sine of the angle, right? 40 times 2, right, times sine of 40, okay? And I'll give you a second to figure that out. What are we getting as the torque? If we're having 40 times 2 times sine of 40, you should be getting something like 51.4 Newton meters, which is the unit for torque. As you would expect, force times the radius equal the equal torque. Let's bring into account geometry in torque. Let's say I have a disk. It has a radius of 0.5 meters. I'm going to do a force at the edge of 30 newtons to cause that to spin. This disc has a mass of 15 kilograms. What is the rotational acceleration? What is alpha? Okay. So I have figured out that, or I should say I know that torque is equal to I alpha, right? And I know that torque is equal to force times the radial arm. Well, force times the radial arm in this case is 30 times 0.5, 15 Newton meters. So that's the torque. So I got that answer. The moment of inertia for a disk you can look up in your tables in your book or online. It's 1/2 mr squared. So I can figure out the moment of inertia, right? 1/2. I said the mass was 15. I said the radius is 0.5. So we square that. So the moment of inertia is what? The moment of inertia is, let me grab another marker here, 1.875. So if I know that torque is equal to 15 Newton meters, equals, and moment of inertia is 1.875. What is the rotational acceleration? Just divide 15 by 1.875. Therefore, alpha is equal to, you get about 8 rads per second squared. Okay, that's just a few examples. Okay. So, in conclusion, remember that if we're talking about in equilibrium, the summation of all the torques has to equal 0. You want to practice the problems in the book and be expert in piecing together the equations. We know that torque is equal to moment of inertia times A, being rads per second squared, rotational acceleration. But we also know that torque is equal to force times the distance sine of angle. Force can be thought of as MA. And in fact, each of these, this bit depends upon its geometry. And this may relate to kinematics For instance, as I said, A is equal to the R, A as in linear acceleration, meters per second squared, times alpha. So I'll make that larger for you. So know how to do that, and all the examples that we've worked through. And good luck.